This is a square wave. Flat tops, instant jumps, corners as sharp as mathematics allows. Nothing about it looks smooth or round. Now watch. One sine wave. Add a smaller, faster one. Keep going, and the smooth, round, endlessly curving sines organize themselves into flat tops and vertical jumps. That is Fourier's claim, the boldest in engineering mathematics. Every periodic signal, no matter how jagged, is a sum of spinning circles. This episode proves it, builds it, and finds the recipe. Here is the claim written down, and notice it is built entirely from episode 1. Every term is a spinning arrow, e to the jk omega not t. 3 ingredients. The fundamental frequency, omega naught, the spinner that completes exactly one lap per period of the signal. The harmonic number k, spinners locked to 2 laps, 3 laps, k laps per period. Only these frequencies are allowed, anything else wouldn't repeat with the signal. And the coefficient ck, the recipe card, how much of each spinner, and at what starting angle? Negative k? Episode 1 told you, just the clockwise spinners that keep the sum real. The claim is stated. The only question that matters is, given a signal, how do we find its recipe? Here is the key fact, and it deserves a slow look. Take any two spinners and average their product over one period. If their speeds differ, the product is itself a spinner, it goes around, and averages to exactly 0. But if the speeds match, the spins cancel, the product freezes at 1, and the average is 1. Different spinners are invisible to each other. Mathematicians call it orthogonality, which turns this integral into a tuned detector. Multiply the whole signal by e to the minus jk omega naught t, the counterspinner for harmonic k, and average. Every component of the signal except harmonic k still spins, and averages away. Harmonic k alone is frozen, and what remains is its coefficient. That is the analysis equation, not a formula to memorize, but a radio dial. Tune to k, and ck comes out. So the pair is complete. The synthesis sum builds the signal from spinners. The analysis integral tunes in to measure each one. Everything else in this episode is just using the dial. Now build the square wave for real. Each circle is one harmonic, its radius is the coefficient, 4 over n pi. Each circle rides on the tip of the one before it. Chain them together, and the final tip carries the whole sum. Set them spinning, the first at the fundamental, the next at 3 times the speed, then 5, 7, 9, 11. Watch the tip's height, traced against time. 6 circles, and the square wave is already unmistakable. Notice something at the jumps, though. The trace overshoots a little horn at every corner. Add more circles and the horn gets narrower, but never shorter. It locks at about 9% of the jump. That is the Gibbs phenomenon, the price of building a discontinuity out of smooth spinners. You cannot fire it. You can only squeeze it thinner. There is a second way to draw everything we just built, forget time, and plot the recipe itself. Coefficient magnitude against harmonic number. This is the line spectrum, the signal's fingerprint. Read the fingerprint like an engineer. Even harmonics, missing, that's the signal's half-wave symmetry showing up. The heights fall off only as 1 over k, and that slow decay is exactly what sharp corners cost. Smooth signals die fast in frequency, jagged ones ring on forever. And the spectrum is mirror symmetric, because episode 1's counterspinners always come in pairs for a real signal. One more gift, Parseval's theorem. The signal's average power equals the sum of the powers of its harmonics. Power is conserved between the two pictures. Time and frequency are two views of one object, keeping the same books. Time to use the dial ourselves, exam style. The ±1 square wave, period t, odd symmetry. Find every ck. Set up the detector. The signal is +1 on the first half period, -1 on the second. Split the integral accordingly. Carry out both integrals and combine. The algebra collapses to 1 minus e to the minus jk pi over jk pi. And e to the minus jk pi is just -1 to the k. Episode 1 again, half a lap per unit of k. Even k, the numerator vanishes 0, exactly as the spectrum showed. Odd k, 2 over jk pi. The j means every harmonic is a pure sine odd coefficients for an odd signal. Magnitude 2 over k pi, falling is 1 over k. Every feature we saw is now on paper. Check against the movie. Converting to the sine series gives amplitudes 4 over n pi, the circle radii from the epicycle scene. The pictures and the algebra agree, as they must. The number to remember, 9%. The Gibbs overshoot at every jump. You can squeeze it thinner with more harmonics, but never shorter. It is the permanent price of building corners from circles. Next episode, the biggest step in the series, we let the period go to infinity, and the Fourier series becomes the Fourier transform.